Hello everyone, Aaron here. Welcome back to Leetcode. Today we are doing the time-based key value store problem. Jumping right in, design a time-based key value data structure that can store multiple values for the same key at different timestamps and retrieve the key's value at a certain timestamp. Implement the TimeMap class. TimeMap initializes it, makes sense. Set the key to a value at a specific time. Get the key at a specific time, returns a value such that set was called previously with timestamp previous less than or equal to timestamp. If there are multiple such values, it returns the value associated with the largest timestamp group. So example, if we set it at time 1 and at time 3 and we ask at time 2, we should get the value that it was set at time 1 because it hasn't yet been updated to be the time at time 3. So this is a bit of a run through of it. So we store foo with bar at time 1. We get foo at time 1. We get foo at time 3. Both of those are bar just because of how it's been done. Foo bar 2, so we overwrite what's at foo at time 4. And then we get it at 4, it's now bar 2. We get it at 5, it's but still bar 2. If we were to call it again at time 2, I'm sure it would still be bar. The key lengths and value lengths are small, but these are just strings. It'll be a Python dictionary. We are fine. Key and value, again, we're fine. Timestamp is a small number. All the timestamps are set are strictly increasing. That's good to know. So here, what we want to do, well, what we can assume is that if I've been given a set at time 1, I'm never going to be given a set at time 0 or 1 again, because it's always going to be moving forward through time. And some bound on the number of set and get calls. So I guess the only complexity is how we store. Well, okay, at the high level, the storage is easy. You have a key and you have a value. The problem is we have multiple values, so we're going to throw them in a list or something like that. The trick is, how do we know which value to retrieve? Easy answer. We store them as tuples in a list of timestamp value. And when we are asked the particular value at a particular time, we just scan the list until we find the highest time that is prior to the retrieval time. Or equal to. Higher or equal to the retrieval time. That seems straightforward enough. We can do that. I am a little worried it might be a bit slow. That scan could be slow. If we have a lot of different time sets for one key, that list could get very long. Better would be to do it in a binary search tree where the keys are the times and we're looking for the largest key, which is less than the timestamp we're currently searching for, but that involves writing an entire binary search tree, so I'm not going to do that until I know it's too slow. So let's create an items dictionary. And then what we want to do is do self.items key equals self.items.get key empty list. In fact, I can do this with a import collections of default dict with a list, append timestamp value. That seems easy enough. And then down here, what we want to do, this is guaranteed to return a string. That doesn't seem right. Unless, are we guaranteed that we will Oh, no, we want to return the empty string. So if key in self.items key define value at no, hang on. Times and values is self.items key, else return empty. So if the key is there, we need to do some work to extract which value we want. Otherwise, we're just going to return the empty list because it doesn't exist at all. Empty string, sorry, because that's apparently the correct thing to do. I'm not sure it is, but that's what the spec says, and we're implementing the spec. So for time value in those. Now, the reason I'm happy to iterate through these in order is because we're always appending onto the end, and we know that the timestamp is monotonically increasing. So the items in this list are monotonically increasing in time. Val is the empty string. If time is less than or equal to timestamp, val is value, else break, return val. So what this does is it looks at every time and value. If the time is less than or equal to the timestamp, it updates the value because that's the latest thing we've seen, which must have been set. As soon as we've gone past the timestamp, stop. We don't want to continue any further. We've found the latest thing, which is either an empty string or the value that was stored. In either case, we want to return it. Let's give this a little go. Now, there's a chance I made a mistake here, but apparently I haven't. That looks promising. How many example test cases do I get? Just the one, isn't it? Do I want to do anything more? No, I think the logic is good. The problem is going to be time if this is too slow. So let's test it and see if it's too slow. It's looking pretty slow. Yeah, time limit exceeded. So here, I can't just do this. I need to have a binary search tree, basically. Root is none. This is pretty trivial actually, but that's the class BST node. Problem is I don't know how default dict actually initializes itself. But whatever, that'll be fine. Insert self val key val. If self.root is none, self.root is equal to a BST node with key val. Yeah, that's fine. Else self.root.insert key val. Get largest smaller self key. If self.root is none, return none, else self.root.get largest smaller self. Oops, I don't need the self there. Just key. Right, so that's just the wrapper. The reason I'm doing the wrapper is because I think this is going to be called in such a way that I need something to create an empty tree. Key self key value left equals none, right equals none. Self dot key is key. Self dot value self dot left equals left. Self dot right equals right. Insert self key value. Actually, how do I want to do this? No, I think I want to leave that as it is here. I need to be a little more clever. Else, what I want to do is current is self.root. If key is less than, in fact, no, hang on. While true. Current is less than self. Current dot value is equal to, sorry, current dot key is equal to key, current dot value equals value, break. Now if current dot key is less than the current key, current dot left. I'm just trying to think the best way to do this because I've not written a binary search tree insert in a while, and I'm used to doing it in a purely functional way. Hang on, so if car is none, prev, oh gosh, no, hang on. No, I don't want to do that. I don't want to do any of this previousness business. If cur.left is none. So if I'm looking at the current node and I know I need to go left. If the left is none, what I want to do is cur.left is bst node key value, key val, else cur, and then I want to break. Car is car.left, and then I want to loop around again. Otherwise, if car.right is none, car.right is a BST node with a key value, break, else car is car.right. All right, that should work. If I'm looking at a binary search tree, why did I do that? If I'm looking at a binary search tree, I'm focusing on something. If it's the key is equal to that, I just want to replace it. That should never happen in this particular case, but it makes the logic easier if I handle the case. If it's smaller, then I want to go left. If it's larger, I want to go right. If I can't go left, great, just insert a new node there. Oh, hang on, this gets really complicated really fast. Because I know I'm always inserting on the left. I'm just going to end up with a really deep binary search tree, aren't I? I need a self-balancing binary search tree. Ew. God, that's going to be awful to write. Is there something I can do differently? You know what? Rather than do this business, I'm not going to do that. Delete it correctly. Maybe I can do a binary search. I know they're in order. Left is 0. Right is len times and values is self.items key. And then I want to do while true, in fact no, while left is strictly less than right. Mid is left plus right over 2. Times and values mid 0. If timestamp is less, in fact, no, let's do it. Timestamp. Okay, so now we've got a slight question. How do I want to do a binary search for this? I'm looking for the largest value that is less than or equal to the current timestamp. So if the timestamp is less than that value, I need to go right. Sorry, no, if the timestamp is less than the mid, I need to go left. So right gets set to mid. Else left gets set to mid. No, left gets set to mid because I want to keep this in the search now. And then when I'm done, these have converged. So then I want to do problem is I don't even know if it's there. If times and values left 0 is greater than timestamp, return empty string. Otherwise, I want to return times and values left 1. So is this the correct binary search? Let's think about this. Let's say I have... Oh heck, let's just run the code. I should think about this because there's a good chance I'll get stuck in an infinite loop here. Binary search is a... I'm stuck in an infinite loop here. So I've got a 1 and a... Yeah. Let's start printing it out. Print left, right, mid. Hang on. Count is 0. Count plus equals 1. If count is greater than 10, break. Because it's going to time out again, and I can't even stop it. Now it's running. Just wondering if Python has a binary search somewhere in the standard library. That would be nice. Oh, come on. Hurry up and time out. While right minus left is greater than or equal to 1. Let's try that. Why? Hang on. Why is it doing so many searches? That's not right. Right, left. Right minus left is 1. Oh, that should be greater than 1. That's better. Now the question becomes, I don't need this count anymore. I kind of want to know what happens if I completely heavily load this thing. Take this. So 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see if this works. Shoot. Do a set. 1, 2, 3. Is that correct? Yes. So it does 10, 5, 5, 2, 2, 1. Yeah, that looks like it's doing the right kind of search, which is good. Let's do it without the printing now. Let's submit it again. This time we've got a login search here rather than an order in search. There we go. Excellent. So this one was a little bit tricky just because you couldn't do the naive thing with the list. You had to remember to binary search your list, which is fair enough. I knew going in that the naive approach was likely to be too slow, but I was just really hoping it would not be too slow. The designers of the question saw through my little plan. Anyway, I think that's it from me today. I hope you enjoyed the video. If you did, do remember to like, comment, subscribe, all of that good stuff. Convince the algorithm that I'm still making decent content. Hopefully you still think I am making decent content. And on that, I think I will see you next time. Bye.